Welcome back to the concepts of friction. In the previous experiment, we were only focused on understanding what is static friction or friction of an object at rest. We were not concerned about the factors that affect it. For example, why is it not moving even when there is an applied force? Why is the block not getting separated from the trolley car with small forces? What is happening between the two surfaces? What is happening at the microscopic level? We did not address all that. Now we are going to work on the factors affecting friction, and in fact the first factor we are going to check is the effect of roughness. So during this activity and the next activities following on, we will be understanding the microscopic level of friction with few experiments. Now for this experiment, I need a block. We have arranged a hook over here. We need a spring balance. You can use the traditional one, or this is a little bit better and more sturdy. It's called acrylic spring balance. So you can use any of this. This particular one is 0.5 Newton capacity. I'm sorry, it's actually 5 Newton capacity or 500 gram force. And then I need a smooth surface. I have this plant which is smooth, and I also need a rough surface. I have this huge wooden block that we use for our drilling and everything. I can use this as the rough surface. If you don't have such things available, you can just look around in your classroom or in your house. So you'll find definitely two surfaces that are smooth and rough. Maybe the counter table, a granite table could be used as a smooth surface. Maybe your balcony base surface could be a rough surface. Just look around to find two surfaces of different roughness. And I'm also going to use these metal blocks to add weights. Each of this metal block is around 200 grams. So I'll be using them as an extra weight so that I can see better results in the spring balance. Now, I want to give you the observations first, and after that we'll proceed with the experiment. Now let's look at the first observation. Spring balance reading on a smooth surface equal to, number 2, spring balance reading on a rough surface. On a rough surface. These are the two data points that we'll be using for our experiment. Now, before we proceed to this, can you make a prediction? Imagine you have a huge metal almirah and you want to push it on a surface to move it. Where do you think it is easy to push? Is it easy to push on a smooth surface, or is it easy to push on a rough surface? Think about it, and the answer is what you'll be seeing in this experiment too. The smooth surface has less frictional force, so the heavy object can be easily pushed on it. And compared with rough surface, always it's easy to push on smooth surfaces. Later we'll analyze this result in much more detail, but first let's look into the experiment. Right, so we have our block over here and we have a very smooth surface and the spring balance. I connected this block with our spring balance using a thread. Now to get clear results, I want to add additional weights on top of it. We are going to use the same weights for both the experiments. That means on the smooth surface and the rough surface. What I'm trying to point is the only thing that we are changing is the surface roughness. The weights do not change, the block do not change, the spring balance do not change. Nothing changes except the surface. Now look at this reading and always try to keep it horizontal. Now I'm pulling it. When does the object move? It's simple. The marker of the spring balance reaches a maximum value and drops. So observe carefully to that maximum value. I will be telling you what that reading is. But anyway, I'm applying the force. Whenever the object starts to move, just about to start to move, you see this marker to jump a little high and then drop. So I'm pulling it. Right now it's showing 1 Newton Object is still not moving. Now it should, yes. One more time. I hope you have seen that. It went to around 1.3 newtons and then quickly dropped as the object was moving. The maximum static friction is 1.3 newtons. When the body or the object starts to move, you don't need a lot of force. This is an important concept, people. When the object is moving, we call it kinetic friction. That is of lesser value than the maximum static friction. That means 1.3 is the static friction, kinetic friction is way smaller than that. We are not worried about the movement friction, the kinetic friction. We only want to see the maximum static friction. So I am repeating the experiment. Please observe one more time. This is 0.5 newtons. Now it's approximately 1 newton. It's 1.1, 1.2, and around 1.3 newtons it starts to move. Okay, so that is the maximum static friction on a smooth surface. Now we'll put this surface aside. In that place, I'm going to use our rough surface. So this is very rough. I'm going to place our entire assembly over here, and then I'm going to pull it again keeping it horizontal. 0.5, that is 1. 1.5, as you can see, it's 1.5 right now. Around 1.8 newtons. It increases and then the object starts to move. One more time. 0.5, 1, it's 1.5. So around 1.8 newtons the object starts to move, or it went to a maximum value and then it dropped. So that maximum value on your spring balance just when it is about to move is what we are observing here. So let's get back to the board to write these results. Right, so let's look at the readings. For our smooth surface, the surface that we used in the first case, it was 1.3 newtons. That was the limiting friction or the maximum static friction. Whereas on the rough surface, it was 1.8 newtons. So clearly, more force is required to move objects on rough surfaces and less force is required to move on smoother surfaces. Or in other words, frictional force on rough surfaces is more, whereas frictional force on smooth surface is less. Now let's try to understand the reasons behind it. Why does smooth surface has less friction and why does rough surface has more friction? So there are two things you need to understand before we could talk about this. One is called irregularities. Okay, these are called the irregularities. Even though we are saying smooth surface, if you check with them in a microscopic scale, this one also has some irregularities. Let's imagine the smooth surface irregularities are like this. See, it has very little depth. We can call it the crest, we can call it the trough. The gap between the top and the bottom is very little. Whereas, let's call this the smooth surface. And for a rough surface, it could imagine in this fashion. Okay, you can think of it in this way. Now, this is our rough surface. Now, we also need to think about the bottom surface of our block. That also has certain irregularities. So, imagine this is the bottom surface of our block. Now, please check carefully. So, the first factor is number of irregularities. Since rough surface is, like as you know, when you touch it, you can feel that ups and downs. There are definitely more number of irregularities over there. And whereas for smooth surface, the number of irregularities could be less. And second thing is, when this one gets in contact with the other one, there is a possibility of interlocking. What I mean by interlocking is, let's imagine this is the first one and this is the second one. There is a chance that one might get locked inside the other. If the locking is deeper, then separating them would be very, very tough. If the locking is shallow, that means only a little bit of depth of locking, then they can be easily separated. As you can see over here, between our smooth surfaces, between the block and the smooth surface, the locking would happen, but the depth of interlocking is very small. Whereas here, there is a greater chance of deeper interlocking, so more force is required. So to conclude, rough surface has more irregularities, Smooth surface has less irregularities. Whereas the depth of interlocking, that means this trough getting into this trough or this trough getting into this trough, the chances of deeper interlocking is possible in this case, and less interlocking or the locking between the two things is less over here. So I want to use a table to explain all these concepts or to summarize. So the first column I would write is surface type. Second column is number of irregularities. Irregularities in your books, you might also see them as ups and downs. And the third column is depth of interlocking. And last column could be frictional force. So the first one is smooth surface. So number of irregularities could be less. So because of shallow type of surface, we get less depth of interlocking, and because of that, frictional force will also be less or low. And for rough surface, it would be exactly opposite. Number of irregularities could be a lot more, so you can have more number of irregularities. The depth of interlocking could also be deeper, so way more deep, that means more interlocking, and because of these two results, you need more force to break this friction. That means friction force will be very, very high. So here I could use the word low, here I could use the word high. So that's about the effect of roughness. And to conclude, rough surfaces require more energy to create relative motion due to the presence of large number of irregularities and deeper interlocking. So with that, we are done with this topic. Let's look into another one in the next topic.